In our last lessons, we were looking at the exponent laws. We reminded ourselves what exponents were, and the two rules that we looked at were the product rule. When you multiply powers of the same base, you keep the base and add the exponents. And the quotient rule, when you're dividing powers with the same base, you keep the base and subtract the exponents. Today we're going to go a step further and look at another rule, and then combine all these rules in a few examples. So, before we do that, I want you to consider this. You don't need to write this down. This is on your worksheet, but I want you to think about it and look at this before we go to our worksheet. So here we have something inside the brackets, something very special inside the brackets that's being squared. So that thing inside the brackets is being squared. So we have 3 cubed. Well, we know from our definition of 3 cubed, that means 3 being multiplied by itself 3 times. So inside the brackets, 3 cubed means 3 times 3 times 3. But that entire thing, this entire thing, is being squared, which means it's being multiplied by itself. So we have 3 times 3 times 3 times 3 times 3 times 3. Well, if you look at this, then, if we get rid of these boxes, and you say it's the first thing being multiplied by the second thing, we end up with an expression that is 3 times 3 times 3 times 3 times 3 times 3. 3 is being multiplied by itself 6 times. So this is the same as 3 to the power of 6. So it turns out that 3 cubed squared, all squared, equals 3 to the power of 6. So this rule is something called the power rule. And it's where we can start and reference our note. So you see in your note, you have that same thing that I just wrote down, and we get that 3 cubed being raised to another exponent apparently is equal to 3 to the power of 6. So the question is, how can we use the law to make this, to do this in one step instead of having to write out all this stuff? Well, you'll notice that when you have one base that is being raised to 2 exponents, this exponent and this exponent, it's the same as that same base, but these exponents get multiplied. So if you have one, you're raising one power to another, you keep the base and you multiply the exponents, because in this case 3 times 2 is 6. In general, we would say a to the power of m being raised to another exponent means you keep that base a and you multiply those 2 exponents. So let's see this rule or this law in action. So the first one here is 5 to the power of 5, which is in turn being raised to the power of 4. So you keep the base and you multiply these exponents. One exponent to another means you multiply them, so 5 times 4 is 20. The thing is true whether we have a number or a variable. So in B, we have x squared, which is turned around and being raised to the power of 3. And so this becomes x to the power of 2 times 3, 6. Do you think the rule changes If we have a negative base, well, no. We're still keeping the base. So you see how the base stayed at 5, and we multiplied the exponents. Here, the base stayed x, and we multiplied the exponents. So in this one, the base is going to stay -2, but we'll multiply those exponents. 3 times 4 is 12. And I don't care if the exponents are positive or negative, the rule still applies. We're going to keep the base in D, get 3, but now the exponents we're multiplying is a -4 times a 2. So let's remember our rules for multiplying. When we're multiplying a negative times a positive, it is -8. I'll give you a second to try F. 5 to the -1 being raised to the -3. Same rule applies. You're going to keep the base and multiply the exponents. And hopefully you got an answer of 5 to the, and this is -1 times -3. A negative times a negative is a positive. And we get 5 to the power of +3. Do we care if one of the exponents is a 0? No. It just makes our math really easy. What's 5 times 0? 0. Now, when we get to H and I want you to recognize that this is still one exponent being raised to another, except we've got 2 different parts. We've got an x² part and a y to the power of 4 part. But each of them has to get raised to the exponent 3, which means each of them are going to be multiplied by 3. And so it's x², which is being raised to the power of 3. 2 times 3 is 6. And y to the power of 4, which is being raised to the power of 3. So 4 times 3 is 12. We can't go any further and multiply or add these exponents because the bases are different. This base is x and this base is y. The only way you can do those rules is if the base is the same. So if you have more than one exponent being raised to another exponent, each exponent must be multiplied. And finally, in I, we actually have 3 things that need to be raised to the power of 2. We have the number 2 itself, then we have x, and then we have x to the power of 4. Each of these need to be raised to the power of 2, which means we will multiply all of the exponents. 2, while it doesn't look like it has an exponent, actually does. It has the exponent 1. And so when we raise 2 to the power of 1 and square it, we multiply the exponents. 1 times 2 is 2. Similarly, x, which doesn't look like it has an exponent, actually has an exponent 1. So we'll take x and multiply the exponents. 1 times 2 is 2. And finally, y, which does have an exponent 4, and it's being raised to the power of 2. 4 times 2 is 8. So each power needed to be raised to the power of 2, and so each of the exponents needed to be multiplied. I can simplify this last one because I actually know what 2 squared means. 2 squared means 2 times 2, which is 4. And so I'll simplify this to 4x squared y to the power of 8. And again, I can't go any further because I have unlike bases. So, questions on page 126, 5, 6, 8, D, F, and I. That's D, F, and I for each of them. are all practice questions using the power rule. So we'll give you some time to quietly work on that practice. Good luck.